what's up guys? Today we're going to go into machine learning a little bit, and it's going to be a very quick tutorial about implementing your own version of the k nearest neighbor algorithm. So let's get started. Right, so let's get cracking. First thing we need is to open Spider, as we're going to crack on with Python. So I'm already in the folder where I want to work. Not that this is a fundamental requirement. Let's have a look. So I've got a temporary thing here, apparently. Python Anaconda. Am I in the right? Yes, I'm using the right virtual environment. So very quickly, what we're going to do is that we're going to create a key nearest neighbor machine learning algorithm, so that you can then apply it to your own stuff. It's full of libraries that do it for you, but just so that you know what we're doing, basically we are implementing this from scratch. And the reason we want to do it is because this way you have your own custom built machine learning algorithm, and you might understand better how it works and have more knowledge of the basics of it. So let's have a look here. I want to have a new thing. I don't know what this is. Save it, just because I want to make sure. I'm gonna put it in. I'll just put it here. It's not best practice, but and let's call it KNN test. Right, so we've got our document now, and what we need to do is that we need to import NumPy, which is the main library we're going to use, and then we're going to import let me think. No, we might be alright with just this. So well, actually we do need something. As a test, we're going to get from sklearn.neighbors, we're going to, do we need this? No, actually we don't, because I'm going to implement my own, right? So we're just going to import the datasets. Now this is what we're going to use as data from our KNN. It's a standard database, and in particular we're going to get the iris dataset, which is probably the most famous dataset for machine learning stuff. What this is basically is a database that has some measurements done for the iris, the flower, and nothing. That's pretty much it. It's just a database that it associates. I think it has 4 variables like the sepal length, the sepal width, and a couple of other parameters that people have gone around measuring about the iris flower, and different types of iris. So I think we've got 4 categories. And yes, 4 categories, 4 types of iris, perhaps 3, I think it's 4, but anyway, we've got these types of iris, and the objective of the machine learning algorithm that we're going to create, and the one that comes with this sklearn, is to classify an iris, an incoming iris, based on previous examples. So this algorithm is going to learn from examples, and it's going to classify the iris. So say you've got a certain amount of measurements done with certain iris, and we know what they are, so we're going to train our model based on this, and then we're going to feed new ones in, and hopefully we're going to get right responses. How do we test it? Well, we split the data that we've got into training and test. So we take a small part of it and we call it test. Now, we have the measurements for this. So even though it's a test, we know what they should return if we apply our algorithm to it. We're going to use this as a proof that our algorithm works. Oh, don't worry, that was nothing. And yes, and we're going to just test this way by comparing our predictions with the numbers. That's a bit, I'm down there, but you see, I'm going to put myself up here. So annoying, it's just so useless. Alright guys, that's because I want to look at you, I want you to look at me. I don't need, you know what, that's not going to work. As soon as sorry about the noise, I was trying to right, I'll just put myself down here and you focus on the code. Right. Okay, so we are going to do dataset load. We've got loads, but let's stick to Iris, which is quite common. And then we're going to do oh yes, of course. We're going to print this just to show you what this is. Okay, let's run this. Execute in my dedicated console. So we're getting this. This is basically a description of the Iris dataset. As I said, you've got these parameters. You've got these classes, you've got three types of iris, 4 measurements that you take for each data point, for each iris that someone has actually gone out there and measured, and we are going to do something like we need. First of all, we need to get our data into an array. So X now is our array of measurements. Just to show you what our next point look like, we're gonna get as this one, okay? And I'm gonna do it for you. Can you see it? Can you see what this looks like? It looks like an array of measurements, okay? Now, and then on top of that, we are going to have an array. So this, by the way, is an array of arrays because each X is an array of measurements, and all of them are the data points that we've got. Y. What is Y? Y is the target, and by target I mean the labels, all classes. So if we again we have a look at Y0, what we get is let's run this and let's get I0. I mean I0, come on. By the way, the commands I'm using are F5, function 5 and function 9. Function 5 runs the whole thing, function 9 runs one line. Anyway, so this is 0. That means label 0, iris setosa. So we know that data point 0 is an iris setosa, and they're all ordered. So x1 corresponds to y1 and so forth. So we've got 4 measurements and 1 label, and bam 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 bam, we've got an array of measurements and an array of labels corresponding to those measurements. Now, what we're gonna do is we're going to have choose a random you know what, let's see this with a random value that we can retrieve. So say is 1, 2, 3, 4, 5, 6, 7. This is, I could use my clock, my time. I'll tell you what. This is useful to keep it like that because if I use a number, a particular number, then this random value is random, but it's always the same. So it's not really random, because obviously it's not random, but it's always pseudo-random. Whenever you say I want a random number from a computer, bear in mind that it's never random. What usually happens is that either yourself or the machine feeds in something unpredictable like time or constantly changing, so that every time you call the random function, you get a value which is different from what the time you called it before. What we're going to do here is to use this seed so that the pattern that we get looks like random, but we're always going to get the same pattern every time we call it. We want to do this to test, and by test I'll show you later what I mean. And so what we're going to do now, we're going to create a bit of noise. What am I doing here? What I'm doing is that I'm adding some noise to our data. This is basically so that it's basically like saying, right, add some extra bits to our big X, to our data, which is just stuff. It just doesn't. It's not right. Okay, it's not really going to anything. It's just there. It's just there basically to confuse our predictions, to make some noise, some stuff which is not right. This is not necessary to do this tutorial, but I wanted to add it because it's gonna give us a more realistic outcome. In nature, you never get a clear sort of perfect set of data. In particular, because data sets that you might deal with are not as small as this one. And so, say for example, you're analyzing Twitter feeds and things like that, you just don't know the format of the data that you're getting, and you might have some noise in the data. You might have some problems with the measurements. Now, to simulate this, we basically just add some wrong values on purpose, so that we simulate these mistakes that you might have in a data set. Right, so now what we want to do is we want to create some random permutation, okay, that's suggesting here, of the data that we've got. In fact, we want to create a random permutation of integers which have the same size of our data points. Okay. Why we want to do this? So we create randomly permutated ascending sequence of integers. So, say for example, I can't remember how many things I've got in here. I guess I could find out. And do I have? I have 150. Right, I've got 150 bits in my data set, flowers that I've measured, and I want to what do I want to do? Yeah, of course. Yes, I want to create a random permutation. I want to create an array of indices that go from 0 to 150, and I want to scramble them. So instead of having 0, 1, 2, 3, 4, 5 up to 150, I get all these numbers but scrambled around. The reason being that these numbers happen, obviously being a sequence of integers, happen to be the indices of this and this array, and any array that has 150 elements, well, obviously you've got 150 indices and they go in ascending order. Now if I create a scrambled array of these indices, that means that I can do this. I can do bins equals, let's create a variable, call it bins, and let's say it's equals to array split. This is a numpy method, and doing this, we split this indices into 5 bits, into 5 equally large subarrays, and then we do this full train equal np.concatenate, and then I put in bins 0, bins 1, bins 2, and bins 3. What have I just done? Well, what have I just done is basically create an array which is 4/5 the size of this array or this array. You know, these are and the same, by the way. It's just the sum of them have been slightly modified. This is what happens when you add something to an array with this syntax. You just basically do it bitwise, so throughout the array. But what I'm doing here is to concatenate 4 subarrays, and this way I've got what I can say full train. A full train, I could even say full train indices, and then I can have a full test indices, and that is simply bins dot 0. Now what have I got? What I've got, okay, is 2 arrays of indices, which are random scrambled indices, which I can use to pick up a random sequence of data from this guy here and a random set of data from this guy here. And the reason I did this is because I don't have them in any order now. Okay, I have it in a random order. I don't know which ones I'm getting, and I don't know which ones are going here. I don't know which ones are going here. It's not that I say, oh, the first 100 and something goes here and the rest is going here. I mean, of either. I'm just getting, I first scrambled the indices, and then I get some here and some here. Okay, so these are basically just 2 arrays of indices. One to pick test data, one to pick test data, and there we go. Now I want to what I want to do is I want to set up my KNN. Okay, so my k nearest neighbor machine learning algorithm. Okay, I want to actually start to make it. How do I do that? Well, first of all, I need to address the basic method of a k nearest neighbor method, algorithm, which is the distance. K-nearest neighbor works like this. You've got a bunch of data, and you want to train on this data, so that every time you get some new data which has the same format, you find the distance between this incoming test sample and the data that you've got. You choose a certain number of data points in your training data that you want to test against, and say this is 10. And then once you have that, you look at the 10 closest members, okay, in your training set, and you assign a label to the test set, to the incoming new data bit, by giving it the most common label in those data points which are close to this new bit. Now, what do I mean by close? Well, we've seen before that an iris, for example, a data point, is composed by a set of measurements: how big it is, how wide its sepals are, and so forth. So you've got 4 bits here. Okay, this is 4 bits in this case of and these are just labels. This is just, these are just in this case they're numbers, and it's 0, 1, 2, 0, 1, 2. What I want to do is I want to say, right, if I have a training set, okay, all of these guys are indices. I can use these indices to these guys are into one array now. I can just take these indices, pick up data from this set, create an array of data points. So for instance, let's call it full train data equals x, and then we're gonna take this. Okay, so what's happened now? Well, what's happened is that what's happening here? Got a bit of an error. Normal takes 3 and I gave 4. Have I done anything wrong? Yes, I have. I was meant to do this. You happy about it? Yes. Good. So what is this? This is fine. Do this. Oh, look at that! Loads of data points from this guy up here, and these data points, okay, I can say, right, say for example I've got this, okay, this full test indices, so I want to pick up full test data. I'm going to take the obviously labels, and I'm going to take the indices, okay. Now what I want to show you is this. If I say take the first, okay, guy here, and I assume, label 2, I assume that I don't know anything about I will go wrong. I was confused. This is probably. So we've got a training data set and we've got a test data set. Now they're different. If you put these two together, okay, you obtain this. Now this is obviously a bigger bit, and this is smaller. Let's say that I just want to say the first one. This is an array of measurements. Let's say that because of our simulation, we don't wanna we pretend we don't know what the label of this should be. In truth, we can in this case, because this is what we're gonna test it against, but we pretend we don't know. So with this guy, we can say, okay, well, what's the distance between this within this iris? Okay, we can picture these features as coordinates in an n-dimensional space, in this case a 4-dimensional space. So what is the distance between this guy, which has these features, these coordinates, and all of the elements of this full data training that we've seen? Oh, I lost it. This one. Okay, all of these guys. We test the distance with all of these guys, and we keep the shortest. The shortest ones could be the shortest distance overall, or the shortest 10 distances or 20 distances, and that's basically also what the meaning of k and n. It means k, which is like the number, nearest neighbors. Okay. K is basically how many? 1, 2, 10, how many neighbors? And that's it. So now we're just gonna basically, now that we know the gist, so we're just gonna implement it. So first thing we need a function that that tells us the distance. So we're gonna get the Euclidean distance, for example, in 1, in 2. That means we're gonna get two things in, two data points in, and one is gonna be our test, one is gonna be any of them, and then we're gonna run through them so that we get them all. But this is just, we're gonna just test pairs. So the result, bear with me, because we want a running computation for I in range 0 to the length of in 1. We do this because in 1 most likely is an n-dimensional, is a vector. Okay, like these guys, each iris has 4 features, but you might apply to anything, and you don't know how many features your object has. Most likely it's not going to have 1, so you account for it. This is an array. These guys are arrays, are vectors that carry the features of the data point that you're analyzing. So then result is the Euclidean distance. So it's in 1 I plus minus in 2 I, and we square it. Okay, now if you know anything about geometry and arithmetics, you know that this is not really Euclidean distance. True Euclidean distance, okay, should have a square, should square the sum. Now, in machine learning, actually, we don't really care, because the results that we get are comparables. I mean, we're basically just trying to find the closest neighbors here. And so if all of the distances are squared, what happens is that we might have a bias towards the closest neighbors, because the farther away they get, the more their distance is enhanced. But to be honest, that's not necessarily a bad thing. We're really interested in the neighbors which are close. And if distance is pushed away, well, unless the search space is really big and our data points are scattered across a massive search space, then it doesn't really matter. And even then, if this happens, if the search space is big, still, it's not really gonna affect the relativity of the data points. So as this is for what we're concerned about here, doing this, okay, it's not really gonna add much. We'll keep it, okay, just in case, or we'll keep this. We've written anyway. But just to let you know, you can save computational resources and avoid this step. Then, for instance, we can say, okay, but what if we want the absolute distance instead of the Euclidean distance? Well, that's also a valid measure, and why not? We can add it. So now we've got three methods which work for our distance. Okay, so let's say now what we need, well, now we need to actually get the right neighbors. Okay, so define method to get closest neighbors in the training set. What do we need? Okay, let's think about this. We need obviously you need to pass in, so let's say arguments. What do we need here? We need to pass in the training set, okay? And we also need to pass in the number of neighbors to return, okay? Now what else? Well, we need, for instance, the data point. Actually, that's probably the first thing, right? We need the data point we're testing against. So data test point. Okay, we want to predict what this is. So we get a data point. We've got a training set, and we've got a set of numbers that we need to find within the state training set, and we need to choose, basically we need to return them. So get neighbors, let's call it, and let's call this guy x underscore, and let's call this guy in big X, and let's call this guy n. Okay, now x, let's say that I want to make sure that it's an ND array, that is a NumPy array. Why do I want to make sure? Well, because there are nice features of an NP array. I don't even think this might necessarily be useful here. I'll skip it for the moment. But in a more generalized case, you might want to have that, just to make sure that you don't break anything. If you get an error, I can always add it later. Now distance that's what we're going to find. We create an array of zeros. Okay, this is how you make an array of zeros in NumPy. NumPy is probably the best thing ever invented to work with arrays, and that's why I use it for machine learning stuff, and it makes Python so powerful. Just this very library. Sorry, don't want to go off rambling, so let's stick to this. I'm going to create an array of zeros, which is as long as our training set. Okay, in X, and then I'm going to loop through our distances. Use this empty array. This is not multi-dimensional, so I can just do that. This is the same as length. Let's just keep consistency. I'm just kind of showing you all this jargon in Python. Let's just keep things consistent. And we want to say if distances at index I. No, without if, there's no if. It's just distances at index I is going to be equal to what do you guys prefer? What do you think? Euclidean. We just want to test this, so we'll just go with Euclidean. It's going to be equal to Euclidean distance between the data point that we want to test against and our incoming array of training data points at index I. Now, if you're clever, you might start to see why we've done our indices before, because we're going to basically work with indices, okay? And sorted indices and the argsort. No. Argsort. Now argsort, what's gonna do is gonna return an array of indices. Okay, well, let's pass in distances, by the way. Okay, so what's happening here is that I create an empty array of indices. Okay, of zeros. Create an empty array of zeros. Then I'm going to go through it, and I'm going to fill it with distances between fill it with distances between the test point and the data points in training set. Okay, so that's what we're doing, and now we want to sort, get the indices of distances in ascending. What am I doing here? I'm just like getting lost. I'm not gonna touch it. The indices of distances in order of distance. What I mean is that, say for example, I had 3 distances, and one was 1, one was 5, one was 0. What I would get out of argsort, okay, would be this. I would get 2. I would get 0, 1. Do you see what's happening? These are the distances, okay? This is what I get if I call argsort on this. It's gonna give me the indices, so that if I was to do this, then I would get distances arranged in order, in ascending order. So argsort is not doing these two things together. It keeps it basically just returns you the argument as the indices, so that these indices are the indices that of the values in order of increasing value. In this case, the bigger the distance and the bigger the indices, basically. And that's fine. We don't want to now apply this to distances, because we're happy with the indices. We're going to just return them. And let's see why. Sorted indices. That's what we want. And so when we say get neighbors, actually we mean get the indices of the neighbors. And then the last thing you want to do is we want to find a label. We want to assign the label for our data point. And I don't know why this is so far. It's not really good to be there. Aspect. I want to get a label, okay, based on an array of labels that we pass in. This array of labels, okay, is going to be the labels of our training points. So do you remember up here when I was saying, okay, now I've got the indices. If I apply these indices to this, I get data points. If I apply the indices to this, I get the labels. Well, that's precisely what we're going to pass in. We're going to pass in this. For example, how do you call it? Yes, this. Okay, full train in. This is an array of indices that I'm going to use for training. These are the labels. So if I do this, I get the data points of our training data set. And if I do this, I get labels of our data set. So the function that I'm going to create is going to take in that training set of labels and returns the most frequently occurring label in such set. Why? Well, let's think about how. What is that? Yeah, let's think about what we're doing here. We're returning the indices, okay, of our neighbors. We're getting a test data point. We've got a training data set, and we choose how many neighbors to return, and we return the indices of those neighbors. Now, what we can do, okay, is that we can turn these indices into a set of labels. So if, for example, doing this, say this returns into something that we call neighbors indices. Okay, I'm just picturing doing this step equals get neighbors, blah blah blah. And then we can do this, and then we can get an array of indices, of labels, sorry, based on our indices. And these labels are going to be the labels of the neighbor data points that we've just found out. And what we want to do is we want to say, okay, now I know the labels of the k nearest neighbors. What is the most frequent? Because this is how KNN works. If you give it one neighbor, it just returns the label. But if you give it 10 neighbors, it's just going to say, okay, this new data point I'm testing is very close to, I don't know, say 10 neighbors, because that's what I want to check, 10 neighbors. What is the class that is most frequent with these neighbors? What do they tend to be? and then that's the answer. That's the label that we're gonna assign. Now we need one last library for that. That is counter, which I think is in collections, because that's gonna speed up our let's just say data, counter, and labels. So this is an array of labels, which are going to be, I don't know, integers, strings, whatever you want. This counter is gonna return an object that has pairs, basically, and the pairs are the elements, okay, the elements that are in here, and the count of how many times they appear. And what I can do now is that I can find the mode, the most frequent one, by calling data dot most frequent, most common, okay, most common, and then I call 1 on it, because otherwise it's just going to return, I think, the most common ones, and it's like a list, and I don't need that. I'm happy with 1. Now I also need to do this, and the reason I need to do this, in fact, I'm just going to show you what this actually does, because otherwise, let's just do this, okay. Now this is an array. Now if I call data.counter r, okay, and then I do print data most common 1, okay, look at what happens. Counter is not defined. I'll define it, don't worry. This is what we get, okay. We get that 2 is the most common value, and it tells us that that it happens 3 times. So I just want to, I'm interested in the label. I don't want to know how many times it appears. But if I call this, okay, property investment, I'll just leave it there. Now, yeah, sorry, it needs to be inside. That's what we get, okay? That's still not good. We want just 2. Much better, right? So that's why I'm adding this. And then I return it. Okay, now we've got all the methods that we need to create our KNN. So I'm gonna create a variable, call it correct, set it equals to 0, and then I will add a number variable, and I'm gonna set it equal to 10, and probably k number of neighbor. Neighbor's number. Let's be verbose, clearer. And then now that I have this, I'm just going to test our thing. So for I in fold test end, that's how we call them, right? Full test end, yes. Then do what? For all the in our test dataset, okay, remember we split a bit out of the whole dataset, and we decided that we pretend that will pretend not to know what the answers for those are, what the labels for those are, so that we can test our algorithm. And then we're gonna say, right, so let's do big X and I. I is an index, by the way, remember? Full test index. Now is it clear why I did that? I got an array of indices here because, well, now I can just pick up from the initial set what this thing was, and I get the index, and then I get the message. Who is that? No one. And then I get an index, a label, sorry. And the label is in the set of labels, and the index is the same. And this is just the test set, by the way, remember? And then we are going to get the neighbors, right? So let's call it neighbor indices and indices, and we do neighbors, and we pass in the test point. Okay, we pass in the training set. So that's it. That is no, it's not full test. It's full train. We pass in the data set, the training data set. That is, we pretend we don't know what the full test index are. We pretend we don't know what the full test y are. We're just sticking to this chunk of the algorithm. And then finally we say, right, I want 10 neighbors. Return me the best, the indices of the closest 10 neighbors. And then I'm gonna prediction, a y test, just prediction. Prediction is going to be assign label, and assign label is gonna be called it's gonna take in y, which is our label dataset, and of course our full train indices, because as I said, that's all we pretend to know. So we've got our training dataset. Now within this we are only interested in the neighbors that we have that are the closest. So this is get the closest neighbor, and predict what they should do. Predict what the testing data point is based on training labels, or best on closest neighbors. On closest neighbors training labels. And finally we test the accuracy of this. Now how do we do that? Well, do you remember I put a correct here, 0? That's because what I want to do now is that I want to say, okay, now every time our prediction is equal to what the this one should have been like. Remember, we've got our y dot y, and test prediction equal to sorry, that's that's fine. I mean, should I ignore this? I mean, do you see that this is basically where I'm getting it from? So I guess I'll just keep it like this. I could just not do this. I could just put this here, you know, and this there. But I'll keep it separate so that I can, for instance, name it, and you might understand better what this is if it's not clear. This is the test point that is coming in that I want to test, and I'm gonna do this for all the test indices, so all the test points. I get the actual point from the index, and this is the true label that the test point should score. We know this because we split our initial data set. So although we pretend not to know this, the truth is that we do know them. And it's now the point to say, right, you know what? Let's test if our prediction based only on the training gets this right. So is this equals to this, the true label? Well, if it is, then correct goes up 1. If it isn't, well, then obviously it doesn't go up. So we could say that we've got an accuracy point, an accuracy index that is equal to correct divided by full test, the length of full test indices, which is how many we're doing. In fact, this shouldn't go here, it should go outside of the loop, because after the loop is finished and I went through all the test set, the test fold indices, then I will have the total amount of correct answers, and then I can get the accuracy, and then finally I can print the accuracy. Oh, a lot of coding. 0.366666. Now that's actually pretty low. Okay, that means like 40%. Now 40% is not really good for an algorithm, and we might have made some mistakes. Great debugging. I love this stuff. No, I hate it, by the way. But oh well, what can we do? So let's see what we've done. We have a data set that that we get from the, you know what, there is a KNN, okay, in built inside of sklearn. So I'm gonna import it, and it's called kneighbors classifiers, I think. Kneighbors. I hope I don't get the capitals wrong. And that's the same. It's not nice not to get help from these guys. Oh, come on. Can I import? Why? Kneighbors. Yeah. Sorry, my British. Well, I'm Italian anyway, but I live in England, so accuracy score. of course, it's in the metrics bit, isn't it? Brilliant. So now we're gonna test. We're gonna say, right, what if we use the KNN equals this stuff, and we train it with the number of neighbors and matrix Euclidean and KNN dot fit. That's the training thing. Excuse me. And we get full training in this. That's the training and the labels for the training. This basically means create a KNN classifier, train it with the training data set and the labels, the corresponding labels, and then what I want to do is I want to predict. Okay, so the prediction for this should be KNN dot predict, and I want to predict on all of these guys. Okay, so y full test. Okay, and I want to is this right? Yes. No. Why are labels? X is I want to predict, right? And then I want to print the other accuracy, which is this, where I pass in my prediction and what they should really be. Or is it the other way around? You're gonna help me. True predict. Okay, so the true is obviously fold test end, and the prediction is this. Right. What's the problem? Line 113. I don't know what that is. There's nothing there. Oh, okay. Usually they do it when I get some parentheses wrong. Better. Matrix. It's not matrix? Maybe it's matrix. Oh, there we go. Oh, so we've got 0.9, okay, in our benchmark, if you want to say it, if you want to put it that way. And obviously much less up here. So let's debug this together. We have that's also gonna be a nice review. So we imported the libraries that we needed. We loaded our dataset. We then describe our dataset. Then we get the measurements, big X, from this data. We get the target, which is the labels, the classes of this data, and then we create a random seed, and we get a random value from it. Well, I mean, yes, basically, we seed the random number generator of Python of NumPy with this, and then we distort our data slightly at random using a normal distribution of basically just like changing our data, some of our data, and we add some noise. So this is not affecting the data, otherwise it would affect this as well. So this is all fine, must be. This is the same, it would affect this as well, so this is not where the error is. Euclidean distance, this minus this square added to result, return result. That doesn't look wrong. Absolute value. You know what? Let's see. Maybe you know, sometimes you just stare at the screen for so long and you just don't realize. No. Okay, so the distance is not the problem, otherwise this would work, and it doesn't work. So what is this doing? It's returning the most common label. Can we print what this is returning so that I know? Okay, loads of data, lots of twos. Lots of twos. It's fascinating. Okay. Oh, that's interesting. Now I get all ones. Where are we? Where am I calling this? Assign label. So this is an array. Get indices. Okay, one sec. What am I getting here? Right, these are definitely indices. And what am I getting here? Right. So there is some problem here. And our problem seems to be about label. What am I doing wrong? That's not, there's okay, let's ignore this, bring this, and labels. They all look pretty similar to me. They all look the same, don't they? And why is that? So nothing is wrong with this. Okay, this is fine. Oh, what's weird is that all of the labels are the same. Now labels come from this. Okay, 29, 27, 26, 25, 24, 23, 22, 20. Right, something is not right. And Where can that be? I'm getting the neighbor's number. I'm getting the training, the X. See, this is pure live coding, by the way. Nice debugging together. Just going to stop this for a second because otherwise I might keep you there forever, and that's not the purpose of this tutorial. Let me just find, and then I promise I won't solve it. I'll just realize what it is and then switch it back on. So that's oh. Where am I going to stop this? Can I do this? No. And here I am back. There we go. Oh my God. Where am I? There we go. Hello everyone. So the big problem was I've deleted the test I've done to find out. As you can see, it hasn't taken me long, and it was really stupid. Now this is how I found out what it was. Printing stuff is amazing. It's just this. If you want to debug, you print stuff. No, this is not how I found out. This is how I found out. Because, and indices shouldn't be as big as this. So I thought, hold on a second. How long is this? Well, it turns out that this is pretty long. Sorry. In fact, it's as long as our labels, so that's definitely not right. How is that possible? Well, where do we get it from? From here. And what are we sending out? Sorted array of indices. But we don't want the sorted array, we just want a number of it. And how many? Well, the first n. Let's try again. Ooh! See what we've got? The accuracy that we get is exactly the same accuracy as you get with the KNN in this sklearn library. So, to wrap it up very quickly, what we've seen today is how to create your own k-nearest neighbor algorithm. And what I'm just going to do to wrap it up very quickly is that I'm going to create a class. I'm going to call it my knn. In fact, class, so I'll call it my knn. Okay, I'm going to save this document right next to where we are now. knn text. This is going to be called my knn. Okay. Then I'm going to import it here. Let's put it down here. In fact, benchmark, and then custom class. And then very quickly we can port over everything that we've done, okay, basically. Yep. We're gonna port over everything that we've done. This is not, Spider is not the best when it comes to copying and pasting code. But thankfully, it there you go. Thankfully, it right. Let's put this up here, and we also need. So right now I'm not doing anything, because that you know, don't wanna bore you with my voice if I'm not really doing much. I'm just, as you can see, I'm literally just copying everything over. We'll have to change a couple of things, but mostly all of this stuff works. So, so we're just gonna keep it. Now, one thing that I'm going to do is, so what do I want to do? I want to create a simple class that that wraps up what we've done together, so that we've also got our own custom myKNN, and we don't need to rely on external libraries. So you can say, yes, I've got my KNN classifier machine learning algorithm that I built myself. Yay! And what do we need? Well, we need an array to store the elements that our training set. You know, we basically want to go with the same logic of how they built it. How did they build it? Well, they create a classifier by setting the number of neighbors and the metric, the distance, and then they fit, that is, they train it, and where they pass in a training set and a corresponding label set, and then they predict. And then you've also got a nice little function here that gives you accuracy stuff. So what we can do is literally just copy them, and we could have another class, okay, called, for example, how well, if this is my KNN, this is my metrics, and my metrics is going to literally have just this, okay, literally this is going to have a function which is going to be called accuracy score, and it's going to take in, like in their case, two things. They're going to take in a test set, okay, and they're going to take in a fiction set. All right. So the set labels and prediction. So true labels. Let's call them so true labels, prediction set, predicted label. Let's be consistent. Predicted labels and true labels. It takes them in, and what it does this. Okay, it finds out an accuracy that is this. It finds an accuracy and it returns it. Now, correct. Okay. Sorry. For I in range 0 to true label length, then accuracy I need correct, don't I? Correct plus equals 1. Exactly what we did before. We're just re-implementing it here so that we've got our own custom function. We called it, it's in the class myMetrics, and we called it accuracy score. Okay, so don't need this. There is one thing. If true labels I equals predicted labels I, then correct plus equals 1, and then when you finish all the for loop, then get the accuracy and return it. In terms of my KNN, well, this one is a bit different because with the KNN we need to basically store our training sets, okay, which is empty at first, training set x, x, and a training set y. So these are the data points of the training set. These are the labels. They're empty. They don't have anything. Then number of neighbors, and we set it at 1 as a default. And then metric, well, Euclidean. Okay, so that's just a string, and it's just gonna be useful to define the metrics. Now, then, what I want is I want to have a method called getDistance, and this method is not gonna take in anything, and it's gonna return 0. Why? Because it's an empty method. I just put it there so that I get a name for it. I reserve a name and I know it's a method, and that's it. These are the variables that I'm gonna have, okay, in this class. Let's do this. And then I'm going to have methods, okay, helper methods. The Euclidean distance, the true Euclidean distance, the absolute distance, the absolute value distance, and they get neighbors. Now Euclidean distance here, what do I need to do with all of this is add this bit. Okay, I need this because of how Python works, so I need to explicitly pass in the reference to what I'm doing here, okay, to our class. And I'll just do it for everything. No, I'll leave that because I need to edit a few things. Right, so now let's actually start to edit stuff. It's nearly done. It's literally just a matter of quickly defining one last thing and then fixing a few bits. So we've got our method. We then need a constructor, which in Python is called initializer. Let's be British. You call it like this. You define it like this, sorry. Okay. Now we're just basically going to copy their style. What do they get? metric and neighbor number. Okay, so neighbor number, okay, and let's say we get in 1 by default, a metric number we get Euclidean by default. Number is a string, sorry. And then we say, right, so our this one is self too. Our our metric, let's start with the neighbors actually. Our number of neighbors is equals to this, and our metric is equal to this, to whatever you pass in, right? And then we're gonna say, okay, in fact, before I do this, I'm gonna do, right, so we are going to decide what our distance function is gonna be like, and I'm gonna do it with a test. If metric is equal to Euclidean, okay, then our self.getDistance is going to be equal to self.Euclidean, which I already defined. Conversely, else, if metric equals, say, true Euclidean, then our self is equal to the true Euclidean. And finally, else, if metric equals absolute, then our getDistance method, empty method, is going to be equal to distance, absolute distance. Okay, so basically what I'm doing is that I'm saying I'm gonna assign any of this to this, so that this is any of them. And what if they're neither? Well, if they're neither, this is Euclidean, and we're not gonna touch it. But we might give out a warning and say metric not recognized defaulting to Euclidean. And then actually I'm gonna put this everywhere, but not at the end, because at the end we'll just keep the Euclidean, right? So now we've copied their initialization, we've defined our function. Ooh, an indent does not much. Is this what you're trying to tell me? Yes, it is. Now, what we're going to find out is so sorry about that. I had just an interruption, and I had to just stop the video for something that just happened here. But basically, well, what I was saying is that now we've got our initialization, and we can just we've copied their initialization. We've got our distance function, which is dependent on the metric we pass in, and we can select the number of neighbors, which changes variable within this class to keep track of that. Now, what else do we need? Well, we need a fit like they have. So a setter and we're gonna call it, well, let's be different. Let's call it train instead of fit. And what we're gonna train a data set and an incoming data set of labels. Okay, so we've got data points and labels coming in, and then what we do is basically just equal to make the training set x equal incoming training set, and the training set y equals to incoming training set. So now we're set, and now we want to wrap the below into a ML machine learning utility method. That's just gonna be one, to be honest. Prediction. There we go. So correct. I don't need this. We don't need this because we've got it up there. And we need a method. Okay, we need a method. So we're gonna call it predict, and predict is gonna take in a test set. Test set. Now I'm gonna create an empty array of predictions, which is going to be as big as our incoming set. That's just a useless email. I don't really care about, to be honest. And once I have that, then I can go. Well, this is our training set, our test set, and that's not gonna be an index. So actually, you know what? I'm gonna get this out. Len set equals this, and then I'm gonna put it here, and I'm also gonna do in range 0 to len set. So now I is an index. Okay. Good. And what else? This is well, I don't have big X. Big X was our training point. Okay. But in this case, no, sorry, it's our test point. So we're going through a set of them. Cool. Good. Right. Y, true label. Well, true label. What is our true label? True label is our training set. What? No, we don't have a true label actually, do we? Because that was useful for testing, but for the accuracy. But really, this is not this not in this part anymore, so that's we can ignore it. So we want the indices, and the training set is actually self dot train. Oh, come on, done. Right, I hate that. Come on. And self dot number of neighbors. So now I've got my indices, and with my indices I need to go through the training set of labels. I need to get the indices. I need to assign a label, prediction. In fact, these are this. Assign a label, prediction. I don't need this. And so what we do, we get predictions as an empty array, and we go through them, and we assign, we predict, and that's it. And we return it. Return those predictions. Return this array. Right? Predictions. Ooh, that should be it. That should be working. And how do we test it? Well, we go back here. We import. So actually from my k and n import, and we're going to import both. We're going to import my k and n, and also import my metrics. Okay, and then in my k and n we're gonna do a my k and n object, which is equals to my k and n, and then we initialize it with the same stuff as this, and then my k and n is going to have a train method precisely like this. We're going to pass in exactly the same things, and then we're going to have a my y pred, and this is going to be exactly the same my k and n this time, and precisely the same. What do we want? Well, we want to print the accuracy. So we're going to print the accuracy score, but that's going to be my actually import as AS2. We do this because otherwise they have the same name, and we don't really want to have them the same name. So no, actually, what am I doing? This is fine. Sorry, because this is a class that we've got there. So let's say that it's a little bit different from what they have, right? It's you can see that it's a little bit different, because then this is we need to do this. I wonder if I have to. Can I do this? Can I do But there's only one way to find out. What if I just call this my metrics? Accuracy score. So import the accuracy score. I don't know if this is invalid syntax. From my keyman. What about if I do this? Ooh, this may work. AS2. And let's run it. Ooh. Ooh. Okay. Sorry. My Canon is not a package. So actually I'll have to just go down the boring route as mm and then mm dot accuracy score. So I'm gonna put here. Right? Let's do this. Missing one argument, predicted label y. Predicted label y. Well, I'm passing in two things. Oh. Fascinating. I would have thought that that was needed. But it didn't. Okay, brilliant. So there we go. Now we've also got a custom class. And that's it. And it's all done, built for you. So I'll upload the source code to my GitHub. And you'll be able to download it. So just to recap, what we've done is that we've created a custom k nearest neighbor machine learning algorithm that takes in a training set. It takes in a training set of data points, a corresponding training set of labels, and then it predicts based on those some labels for incoming data. To test it, we have taken a bigger data set that we know what it is, we know all the data points and we know the labels, and we've used a portion of this, just a little bit, to create our smaller training set. And then we've got a test set that we actually know what the labels should be, but we pretend we don't know them so that we can predict based just on the training subset, and then check the accuracy by dividing the correct predictions, the number of the correct predictions by the number of the total attempts that we've made. And this is it for me. So let me just bring this up. So please don't just freeze like that forever. Okay. It seems like honestly, guys, honestly, I just want to say goodbye. So I'm just gonna bring this up. Hopefully it's gonna refresh. And there we go. That was quite fun. So yes, good night, guys. Thank you for watching. I'll see you next time.